was in the middle of proving to you that geometric lattices are precisely the lattices of flats of matroids. And so what we did last time is I showed you how to start with a geometric lattice and construct a matrix out of it. So we said that the ground set was going to be the set of atoms of your lattice, and the rank function in the matroid of a set of atoms is the rank function in the lattice of the join of those atoms. So if you want to know the rank of B comma D, you come to the lattice, you join them, and you see what rank that has. So the join of the things in your set so I defined this, and last time we did prove that this was actually a matroid. So last time we proved that this set and this rank function define a matroid. And then what I started doing, but I didn't finish, is to show to you that the lattice of flats of this matroid is the lattice you started with. And that's what we're going to do today. So remember what I did first is I told you that if I wanted to show this isomorphism of posits, I needed a map. So I defined the map, which started with an element of the lattice and gave me an element of the lattice of flats of this matroid. And the way I defined this map is I said that phi of an element of the lattice was equal to, what did I say it was? The set of atoms less than or equal to x in the lattice. So this is a subset of E. And what we showed last time is that this actually is a flat. Show that this is a flat, so it's an element of the lattice of flats of the matroid. Okay. And so what I want to show today is that, okay, so now we have a map from the lattice to the lattice of flats of the matroid, and now I want to show that this is actually an isomorphism. Okay. And so to show that it's an isomorphism, I need to show two things. The first thing is that this map is bijective. So it actually is a bijection of sets. And then the second thing is that phi respects order. And what that means is that if you start with an x less than y in your lattice, then that means that phi of x and phi of y are also comparable in the lattice M, and vice versa. Okay. So this is where we were, and this is what I'm going to do now. So I'm going to show you that this map is bijective and that it respects order. So to show it's bijective, I need to go both ways, right? So first, let's show that it's injective.
Yeah, I'm misspelling bijective, aren't I? Spelling it in Spanish. You shouldn't let me do this.
You get it. It's not terrible for us to read some Spanish.
Injective. Okay. So let's show that phi is injective. Well, suppose that two things in your lattice map to the same guy. Okay. In other words, the atoms less than or equal to x are the atoms less than or equal to y. Well, if you remember, last time I showed, we saw, and actually, this is important enough that I want to keep it somewhere that we'll see it. Last time we saw this, that in a geometric lattice, any element x is the join of the atoms below it. We showed this last time. And this is going to give me this, because it's going to tell me.
So it's the lattice.
Right.
Join.
Right, so basically I just use that, right? And I say, okay, in my lattice, x is the join of the atoms less than or equal to x. But then I'm assuming that these are the same atoms that are less than or equal to y. And then I use my lemma again, and I get that this is y. Okay. So phi of x equals phi of y implies x equals y. So phi is injective. Okay. And the second thing I need to do is to show that phi is surjective. To show that phi is surjective, I need to show that any flat in the lattice of flats is phi of something. So let F be a flat of my matrix. Now, I have a flat in my matroid, and a flat is just some set. Right? In this case, it's a set of, the ground set is the atoms, and so here what I have is just a set of atoms. F is a set of atoms. And I want to say that my set of atoms is phi of something. Well, phi of what would it be? Basically, the natural thing you might try is to show that if it's phi of the join of those atoms. So let's define x to be the join of the atoms. Now,
X. So now X.
so this is an element of my lattice L, right? So again, so this is a little bit confusing because I have two lattices here. But I'm starting with F, which is in the lattice of flats. That means F is a flat. Okay. So it's just a collection, a subset of my ground set. And my ground set is a bunch of atoms. In other words, F is just a bunch of atoms. So now I'm saying take X to be the join in the lattice L of those atoms. And perhaps I should put an L here so that you know that this join that I'm talking about is the join in L. So join of atoms in L. And I claim that phi of x is F. So X is the guy that I'm looking for. Okay. I'm going to do this just by showing the two inclusions. These are both sets of atoms. So let me show one inclusion and then the other one. Okay. Now the easier one is this one. So let's say that you take an element in your flat. Okay. Then that means X is the join for, maybe let me call it alpha so you don't get confused with this F. By definition, X is the join of atoms in F, and alpha appears here.
Yeah.
So alpha joins something is bigger than alpha. Okay. But what is phi of X? Phi of X is the set of atoms less than or equal to X. Well, here's one of them. Phi of X is a set of atoms less than or equal to X, and I just showed you an atom, alpha, which is less than or equal to X. So this guy contains alpha. So that shows my inclusion that F is included in phi of X. And for the opposite inclusion, so you start with some alpha in phi of X. Okay. And I want to show that alpha is in my flat. So let me do this. Well, I'm going to say, since alpha is in phi of X, then well, X is the by definition, alpha being in phi of X means that alpha is less than or equal to X, right? Yeah. And X by definition is the join of the atoms in F. Okay. So I have alpha less than or equal to this guy.
I mean, I understand everything you're saying. These A's, so you're saying A is an F. I mean, so the atoms are bijective, so we can almost identify them with each other. Because before you were saying A was the atoms of L, and we used alpha for phi of X.
I'm sorry, could you ask the question again?
You're saying A is an F, but then you're also kind of were saying A was in the set of atoms of the other thing. I mean, it's the
Which,
same thing.
which it is because
Yeah.
F is a flat
Yeah.
in a matroid whose ground set is a bunch of atoms.
Yeah.
The elements in this matroid
Yeah.
are the atoms.
The elements in a
It's
matroid
just
M
the
is the atoms.
notation is confusing on this proof.
And I don't think it's even the notation. I think it's just kind of a confusing proof because you have these two lattices that, of course, they are very closely related to each other because they're equal. That's what we're about to show.
Yeah.
And
So to differentiate between the two.
right. Yeah. And so what do I want to do now? Well, I have an alpha which is in phi of X, and I want to show that alpha is in my flat. Right? I want to show that alpha is in F. So I say, okay, by definition, alpha is less than or equal to X, which is the join of the atoms in the flat. And now the point that I want to make is that alpha actually is one of the guys in this join. But we don't know that yet. But what I'm going to do is this. I say, well, what happens if
Alpha was.
I join this guy with these? Okay. So what happens if I join alpha with all of these guys? What happens when you join something that is less than something? Whenever you have a x less than y, if you join x and y, it's the least upper bound of x and y.
So either you go up or you
Y.
Yeah.
So because alpha is less than or equal to this guy, then if I join them, I just get the big guy. Okay. And therefore, these guys are the same element in my lattice L, so they have the same rank. rank of alpha join is equal to the rank of this guy. So the same element. These are ranks in my lattice. Okay. But what's this, for example? What's the right-hand side? Well, if you look at the definition of my matroid rank, then you're going to see that this is precisely, by definition, the rank in the matroid of my set F. And what is this expression right here? Again, by definition, this is the rank in the matroid of alpha union F. Okay. So I get this. But what can you tell me if I have F has a certain rank, and then I add alpha to it, and it doesn't increase the rank? Then that means, I mean, remember, F is this is basically the definition of closure. Alpha is in the closure of F. So what's the closure of F? Well, I assume that F is a flat, so it's already closed. Therefore, so I started with an alpha and phi of x, and I showed that alpha is an F. So I get my inclusion, and I get that my map is surjective. Okay. So far, so good. Any questions about that? Okay. So now let's prove that phi respects order. I already showed that phi is actually a bijection from a set to a set, and now I'm going to show that it respects the order. So I need to show the two directions. I start with an x less than y. So first direction, suppose that x is less than y in the lattice. I need to show that phi of x is less than phi of y in the lattice of flats. Okay. Now, just so we don't get confused, what is the order in the lattice of flats of a matroid? Remember that we defined the lattice of flats to be a poset of flats ordered by containment. So saying that phi of x is less than phi of y in a lattice of flats is the same thing as saying phi of x is contained in phi of y. This was the definition of the order in any lattice of flats. So if I start with x less than y, I need to show that phi of x is contained in phi of y. But what is phi of x? Well, by definition, phi of x is the set of atoms less than or equal to x. And phi of y is the set of atoms less than or equal to y. But if an atom is less than or equal to x, then it's also less than or equal to y. So we kind of put it like this. Anything that is an atom less than or equal to x is going to be less than or equal to y. And so, therefore, phi of x is contained in phi of y. Okay?
Question, in the same way, are these strict less than or equal to, or sometimes you're, like up there at the beginning, do we really mean that x is strictly less than?
Well, strict equal and kind of was covered by the previous thing. You know, really.
So that's a good point. I'm being a little bit sloppy here. Because I started with x less than y, and I concluded that phi of x is included in phi of y, but I said I wanted to conclude that it was a strict inclusion, actually.
Why do you need to do that? Why can't you just say less than or equal to all the way through?
The alternative was to say less than or equal to here. let me say that I started doing it this way. Let's finish doing it this way. So how do I show that phi of x is not equal to phi of y? Suppose phi of x is equal to phi of y. Then what can you tell me? Well, phi with bijective. So if phi of x is equal to phi of y, we proved phi is bijective, so x is equal to y, which is a contradiction because I assume that x is less than y. So if phi of x were equal to phi of y, I would have x equals y, and therefore I cannot have equality here. So that's a strict containment. So that's one. And now let's assume that phi of x is contained in phi of y. Okay. And now I want to conclude that x is less than y in my lattice. But I'm going to just do the same argument that I use for injectivity. I'm going to say that by definition x is the join, or not by definition, because of this lemma here, x is the join of the atoms less than x. And y is the join of the atoms less than y. Okay? What this is saying is that the atoms that appear in this join are included in the atoms that appear in this join. Okay? So in this join, I'm just taking the join that I had already and joining more things to it. So therefore, x is going to be less than or equal to y because this join is bigger than this one. How do I know that I don't have equality? Again, if x was equal to y, then phi of x would be equal to phi of y. So, but clearly x is not equal to y. And so therefore, this cannot be an equality. And I had just showed to you that phi respects order. So there we go. That's the proof. And so what we proved is the theorem that a lattice is geometric if and only if it is the lattice of flats of a matroid. Any questions about that? Now this is one of these proofs that, okay, so you saw it already and probably you followed every step that I said. But really, probably you want to look over the notes again and see what it is that I did and even try to do it again yourselves and then you really get to, it's the kind of proof that you understand it better if you do it yourself than if you watch someone else do it. There's a proof. Now,
so you made a comment the other day that these are isomorphic lattices, and the question. So what I'm guessing, I mean, for the lattices to be isomorphic, they're going to end up. If I drew it, I should get the same picture.
Mm-hmm.
So there's not some way that I'm going to get something that looks at all. There might be flipped over or something, but not different. Like the order of things might be rearranged at any given.
right, I mean, how do you know if two lattices are isomorphic? It should be the same picture. Now, the question is, okay, maybe you flip D and C and then you got a picture that's a little bit different.
Right.
But the point is that by relabeling, you should be able to get exactly the same picture. That's what it means for poses to be isomorphic or for lattices to be isomorphic.
So, I mean, are we going to talk about what does it mean for two matroids to have isomorphic lattices of flats? Because we already know that their does not mean that the matroids themselves are isomorphic, right?
It's actually exactly the next thing that I was going to do is ask you, I mean, so what did I show? I showed that theorem, geometric lattices are the same thing
has lattices of flats of matroids. But the question is, for example, we saw already that different graphs can give you the same matroid. And we're going to ask ourselves a similar question now, which is, can different matroids give you the same lattice? And I saw last time that they can, because I saw last time, so we saw last time, that the lattice of flats of the matroid doesn't notice what? It doesn't notice loops, first of all. So we saw that the way that we got this lattice of flats originally was from a matroid that had loops. It had one loop, but we can't see whether this guy has a loop or not. So it doesn't notice loops. And the other thing that we saw is that lattices of flats don't notice parallels.
It's not quite that it doesn't notice the parallel elements, it's just that like it'll merge them into one. Isn't that what happened? Because the loop is just not there. But then when we saw last time, it was like
I see. So
Yeah.
Doesn't differentiate.
Doesn't differentiate between parallels. Doesn't. So that basically, if it has a bunch of, if a matrix has a bunch of parallel elements, when you take the lattice of flats, they all get merged into one element. So it doesn't merge. Let's say it merges parallel elements. And so you do lose some information in going from the matroid to the lattice of flats. You lose the loops, you lose the parallel elements. Okay? But the good news is that that's it. That's all you lose.
So, wait, can I realize I'm putting up on notation.
Sure.
So when you're talking about going from this matroid to LM, it's sort of like we went from the matroid to the lattice to the new matroid back to the lattice. So
Yeah.
I'm lost on who I'm in, who I'm are.
Let's think that you just have one matroid, okay?
Okay.
And the question is, what do you lose?
So what information do you lose?
What information do you lose about the matrix when you go to the lattice?
Okay.
What information about M do you lose going from the matroid to the lattice? In other words, if I give you a lattice and I ask you, can you recover the matroid? Well, you cannot, because you don't know if the matroid had loops, you don't know if it had parallel elements. But that's the only thing that can go wrong. And other than these kind of trivialities, you can actually recover the matroid completely from this picture. But that's all you lose.
Federico, so that means that you're losing like all your dependent sets and in the matrix?
You remember a parallel element. Two elements are parallel if they're dependent on each other.
On each other.
So you don't lose the dependencies of these guys with the other ones.
So you're sort of losing your circuits of like 1 and 2 or something. Yeah.
So what you're doing is exactly that. You're losing your circuits of size 1, which are the loops, and you're losing the circuits of size 2, which are the parallel elements.
So the closure of any element is so. Let's go.
Right. And so, definition. A matroid is simple if it has no loops, it has no parallel elements. has no loops or parallel elements. Well, imagine this. Imagine I tell you a lattice. I give you a geometric lattice, and I tell you, this is the geometric lattice of a simple matroid. Now can you recover the matroid? Well, now you're going to say, okay, what's this bottom thing? This bottom thing is the empty set because there's no loops. What are the elements of the matroid? The elements of the matroid are the rank 1 flats because there's no parallel elements. And so I can really say, I'm going to call the elements of my matroid A, B, C, and D. And each one of them is going to be a single element of the matroid. And how do you recover the rank function of the matroid? Well, in the way that we defined it. The rank of a set of elements in the matroid is going up to the joint and looking up the rank in the lattice. So that means you can recover the whole matroid, assuming that it's simple. And so this theorem is actually stronger. It says that there's a one-to-one correspondence between geometric lattices and simple matroids. So this correspondence is bijective. Geometric lattice, well, from simple matroids to geometric lattices.
Right, don't we also essentially lose colors?
We don't. And this should strike you as a little bit strange because matroids have this nice notion of duality, and you would imagine that whatever happens to the loops happens to the coloops, but actually it just doesn't. So the lattice of flats can tell whether you have coloops, but it cannot tell whether you have loops.
So if you looked at the dual lattice, then you could know if there was loops. If you looked at the lattice of the dual matroid.
So if you look at the lattice of the dual matroid, you can tell if there's loops or not. I wanna say a little bit more about this duality. I will. So this is a huge theorem, right? This basically says that if you want to study matrix, it's the same thing as studying geometric lattices, and it's not just that there's some big relationship between them; they're really the same objects.
What if you don't want to study simple matrix?
Now, why do you want to study simple matroids? Because they're basically the same thing as non-simple matroids. I mean, we already saw that loops kind of play this trivial role where they're just hanging out and not intervening at all. And parallel elements are these guys that are always holding hands and they always do everything together. So I mean,
Just pick one of them to study.
you just pick one of them and it's exactly the same thing. Right? And so, I mean, it's the same thing if any of you have taken any graph theory courses. A lot of the times in graph theory, people assume the graph is simple. And when they say that, they mean you don't have any loops, because who cares about graphs having loops? And then you don't have any parallel edges, because why do you care about having parallel edges? One is enough. So, and this is also the source of the terminology simple, because it comes from the fact that, I mean, all the interesting things about a matroid are already there if you simplify and you forget the loops, and you forget and you merge the parallel classes.
In a graph, what are the parallel edges?
In a graph, the parallel edges are the ones that go like this.
Oh yeah.
And the point is, if you want to study walks in a graph, then once you can go walk in one way, you don't need other ways to walk. I mean, there's reasons to consider non-simple graphs, but for most practical purposes, the simple case is enough. And I actually want to teach you a little bit of terminology. Which you will see in the literature. So if you look up old books in matroid theory, they might never say the word matroid.
Matroid is a pretty controversial word, actually. So, the person that I learned matroids from was Giancarlo Roda, who was one of the very influential people in matroid theory. And he used to say that that was the most cacophonous word in the English language, matroid. I don't know if you know the word cacophony, but cacophony is when you have like a ridiculous amount of noise and very dissonant noise. And he really think, and probably you've noticed it by now, that whenever you tell people you're studying matroids, people think, well, what kind of a name is that? Who thought of that? And this was his point: is if you want to start a reputable discipline, you should start by giving it a good name. And he really, any paper that he wrote, he never said the word matroid. He used the word combinatorial geometry. I think sounds more reasonable. Or he would just say geometry. But actually, he called these combinatorial pre-geometries. Okay. And the reason is that what he called combinatorial geometries were the simple matroids. Simple matroids. And I tell you this for two reasons. First, because you're going to see this in the literature. So when you see combinatorial geometry, this is what this is talking about. But also this should illustrate to you that in many people's eyes, the important guys are the simple matroids, and pre-geometry is an auxiliary thing that, I mean, a point of view is that the interesting thing are simple matroids. And you only care about matroids because you want the notion of loops that is dual to coloops. So for duality, for you to have duality, you need loops because you have coloops. So this thing behaves well under duality. But for a lot of things, the simple matroid is what you care about. And so this is one of these big historical coincidences where some people were studying these things that they wanted to call, I mean, they were studying linear independence, and other people were studying lattice theory, and they stumbled into the same object, and they thought, okay, this is probably worth studying if we never talk to each other and we define the same thing.
So where did the word matroid come from? Matrix.
So the word matroid comes from the fact that it was supposed to be some generalization of what happens with matrices. But that already, I think, is a little bit short-sighted because even... So the point is that it comes from linear matroids that come from vector configurations. But we already saw that linear matroids, you don't necessarily want to think of a linear matroid as the matroid of columns of a matrix, which is how people used to think about it. It might be more natural to study it as the matroid of a subspace.
Yeah.
But I mean, this was the...
So that's all there is to it? It's as simple as that?
Yeah.
That's people were just like, well, for me, something roided sounds good.
Whitney coined the term.
I'm sorry?
Whitney coined the term matroid.
Yeah. I guess Whitney coined the term, and Roda was Whitney's biggest fan, but I guess he just didn't agree with the... And I agree with him, actually, because already when you call matroids, that means people like to call cotransversal matroids strict gamoids. And then there's this thing called gamoids and this thing called greedoids and antimatroids, and I mean, you're stuck with these Android objects just because someone decided to call it matroids.
Bad Star Wars episode, sure,
Yeah. Okay. But anyway, so that's good. Matroids are basically the same thing as geometric lattices. And I want to go back to a question that Chris asked me last time, which is that I proved to you that geometric lattices are atomic. I mean, this was part of the definition, right? And Chris asked whether they were also coatomic, so that maybe you can flip them over and they'll still be geometric. So the question was that, are geometric lattices are they coatomic? And what does coatomic mean? Well, if you're going to call atoms the guys in the first floor, then coatoms are going to be the guys in the next to last floor. Atomic means that everything is a join of atoms. So coatomic means that everything is a meet of coatoms. And it turns out this is true, actually. they are coatomic. Proposition. Geometric lattices are coatomic. This might be a little bit surprising to you because I just told you that the duality is not just, I mean, if you have a matroid and the lattice of flats, then if you want the dual matroid and its lattice of flats, you cannot just flip the lattice, which is the thing you might want to hope is true.
That's what people use the word duality for lattices.
Yeah, and actually, there is a notion of dual lattices, and the dual of a lattice is going like this to it. But then the duality of matrices does not correspond to duality of lattices. And so this might surprise you that they're atomic and they're coatomic also, but they just don't. The problem is submodularity becomes supermodularity.
So duality of lattices implies just flipping the lattice upside down, but coatomic does not imply flipping it upside down.
Right.
Okay.
Coatomic is just this property that says that every element is a meet of guys on the top floor. So I'm going to say this. I'm going to say something stronger, which is that every flat of rank, the top rank is R. If you have a flat of rank R minus K, so this is K floors down, then you can obtain it by intersecting K coatoms. Is the meet of K coatoms. Questions?
Problem with your picture?
Is there a problem here?
The guy on the right on the second floor?
This guy
Yeah.
is a meet of itself. Because these are the coatoms.
Yeah. Okay. Oh. Yeah.
So in this floor, it's trivial that each one of these guys is the meet of itself. Then if you want these guys, you just need, everyone is a meet of two coatoms. If you want these guys, they're a meet of three coatoms, and so on. Every flat of rank R minus K is the meet of K coatoms.
No. Then what about A?
So for example, A is the meet of these two coatoms.
Oh, that's right. It doesn't need to be unique.
It's not unique, right? So it can be these two, it can be these two, it can be these two.
Yeah. Okay.
So I'm definitely not claiming that this is unique. I'm claiming that it's the meet of some K coatoms. So before you go to prove this, you want to think about what the coatoms are here. Okay. What is a coatom in the lattice of flats? Well, it's a flat of rank R minus 1, right? Now, if you think about this for a little bit, what does it mean to be a flat of rank R minus 1? It means we have a set that has rank R minus 1, and if you add anything to it, you get rank R, right? But rank R means spanning. So what it means is something that is not spanning, but as soon as you add anything else to it, it becomes spanning. In other words, it's a maximal thing, maximal non-spanning thing. So they're non-spanning, but you add anything to them and they become spanning. And there's a name for these guys. They're called hyperplanes. Which is suggestive. A hyperplane is, in geometry, is a subspace of dimension codimension 1. So if you add anything else to it, then you get to span the whole space. Okay, so how do you do this? You induct. You induct on K, where K equals 1, as I said, is trivial. Because every coatom is just a join of itself, a meet of itself. So now let X be a flat of rank R minus K. So what I'm going to do is assume it for K minus 1 and prove it for K. So X is a flat of rank R minus K. If you want to use the induction hypothesis, then what you want is to go one step up. You already proved it for the floor for co-floor 1, co-rank 1, co-rank 2, co-rank 3, co-rank k minus 1. Now you want to prove it for co-rank k. So what you want to do is move one step up and then apply induction hypothesis. Okay. So if I have a flat of rank r minus k, how can I step up to the next rank? If I have a flat, I'm going to just add some random element and take closure. And that's going to bring me one step up. So if I take y, which is not in x, then the rank of x union y is the rank of x plus 1, because x is a flat. And so therefore, the closure of x union y.
Okay, so now that we showed that geometric lattices are simple matroids, you can talk about closure, or because this
Well, I mean,
it's all lattice language, but we already kind of showed that we can go.
yeah. So this is lattice language,
Yeah.
and this is matroid language, and
Yeah.
so by now you believe me that these two statements are actually this one is stronger than this one, and I'm going to prove this one, which is a statement about matroids. So I can use rank, closure, everything. So the rank of x union y is r of x plus 1, which is r minus k plus 1, which is r minus k minus 1. And so this guy is a flat of rank r minus k minus 1. Let's call it maybe big Y. Okay. So I can use my induction hypothesis to say, well, Y has co-rank k minus 1, and so I can write it in the desired way. So I can write Y as an intersection of k minus 1 hyperplanes. Now perhaps I should do one thing, which is, remember that the meet in lattice of flats is intersection. We proved this. And so actually, if I wanted to keep this to be a statement about matroids, then I should write intersection. Meet is lattice language, intersection is matroid language. So I write my flat Y as an intersection of these guys. Okay? Now, again, the idea is that here's my lattice of flats. Here's the guy X that I want to obtain as an intersection of hyperplanes. So what I did is I moved up one step, and I wrote Y in the way that I want to write it. Okay? Now what I want to do is basically add another hyperplane to the intersection and get to X. Okay? So what is the other plane that I'm going to add? Well, I'm going to write two cases. The first case is that E minus Y is a flat. And the second case is that it's not. If E minus Y is a flat, then it's a hyperplane, right? Because it's the whole set minus one thing. If it's a flat, it's maximal. So I'm going to define the case hyperplane to be E minus Y. Now,
I don't understand that. Can you take one more shot at that?
so what I'm saying is, here's E, right? And then E minus Y is subtracting. So maybe another way of saying it is that there's two cases. The rank of E minus Y is R minus 1, or it's R.
Okay.
Right? Because this is the whole set minus one element. If it's R minus 1,
I'm sorry. We're talking about little y again. That's where I got lost.
oh yeah, this is little y.
No, you drew it right. I just didn't pick it up. Got it.
This is little y. So if the rank of this guy is R minus 1, then it has rank R minus 1, and the only thing that contains it is E. It has rank R. So that makes this guy a hyperplane, maximal, non-spanning. So I take this to be my hyperplane. If the rank of E minus Y is R, that means that A minus y is spanning. So I have x inside A minus y. Remember that y is not an element of x. Where this guy is not spanning because the rank of x is r minus k, and this guy is spanning. So if I have something non-spanning inside something spanning, I can basically add as much as possible to this guy to make it maximal non-spanning. So I'm going to find something in between, which is maximal non-spanning. I can do that because this one is non-spanning, and I add things to it until I get something that's spanning. Until I get something that's maximal non-spanning. Okay? Because it's maximal non-spanning, it's a hyperplane. I claim that this is the hyperplane that you need to add to the intersection. And so in other words, this is the intersection that you want. And I'm basically out of time, but I want to quickly tell you the reason. The reason is that by the inclusions that you see on this board, you're going to get that x is in this guy and this guy is in y. This is obvious. And x is in y by assumption, and x is in hk by assumption. So what I have here is these two guys are, this guy has rank the difference in rank here is 1. So this is a cover relation. So this guy has to be equal to this one or to this one. Because this guy has rank r minus k, and this guy has rank r minus k plus 1. So this is a cover relation, and this guy has to be equal to this one or to this one. And this guy is not equal to y because little y is here and little y is not in here. Here you don't have little y. Here you do have little y. You don't have little y here because hk is contained in E minus y. So if these guys are not equal, then these guys are equal. And that shows you that geometric lattices are coatomic, even though they're not. Even though geometric lattices are not a class that behaves so well in their duality.
So the opposite lattice isn't necessarily geometric. So,
no, if you take the dual of a geometric lattice, you're not going to get a geometric lattice in general. Okay, let's stop there.